I would be.
I know.
All right, 2 practice problems. Go. Feel free to solve the left one, either method. I would recommend the product rule, but if you were to multiply that puppy out, okay, you. But the one on the right, you definitely got to fire some quotient rule action.
Oh, this is from 8th grade. Oh, it still fits me. Miraculously. Nice.
Remember on the quotient rule, you're probably not there yet, but simplify the numerators, not the denominators. Leave the denominators alone. Remember early on, there's really 2 components to each of these problems. One is the general setup. Do you know how to apply the product rule? Do you know how to apply the quotient rule? The second part of the problem involves being able to simplify it. Gracias. Okay, let's see. 3x squared minus 4x times 5x minus 4 plus x cubed minus 2x squared plus 7 times 5. How'd I do? Okay, good. Now yours might be in the other order. It doesn't matter because 1 plus 2 same thing as 2 plus 1. But I'm okay? All right, good. So that's the first part of that. Right now, that's what I'm most concerned about. The rest of this will come from practice. it is some basic algebra stuff. So 15x cubed minus 20x squared minus 12x squared plus 16x plus 5x cubed minus 10x squared plus 35, yes? Good. 20x cubed. Negative 20, negative 32, negative 42x squared. Plus 16x plus 35. Yeah, good? Good? All right. Problems, questions, concerns? Easy peasy? Again, you may have screwed up because I saw a lot of different answers. Right now, this is what's most important to me. The rest of that stuff will come through practice. It's probably been a while since you multiplied out a binomial. All right, make some room here. And let's see how ugly this quotient rule gets. It's not bad? No. Good. All right. Let's see. Equals. Denominator squared. Bring the denominator up to the top. Times the derivative of the numerator. Minus big honk in bracket. Numerator times derivative of the denominator. Oh, that's not bad. How'd I do? Good. Okay, leave the denominator alone. You're going to be tempted sometimes. Don't. 3x squared plus 6 minus 6x squared minus plus 12x, which is negative 3x squared plus 12x plus 6 all over x squared plus 2 squared. Okay. Now, if you're feeling saucy, you could factor out a GCF in that numerator, and in fact, that quadratic might factor, but it won't help us in this case. You're not going to have a term that's an x squared plus 2, so we'll just stop there. Okay, we're good? Beautiful. All right, let's do some chain rule. We have 2 more techniques for taking derivatives, and then we're done. So I've kind of been taking a shotgun approach, meaning I'm just blasting you with all this information. Then you're going to start or continue to practice until this stuff kind of becomes second nature. Okay, so chain rule. It's going to allow us to take the derivative of composite functions. We haven't done that yet. We've done addition, subtraction, multiplication, and division, but no composite functions. Then we'll start talking about what's involved in simplifying some ugly, nasty derivatives. We'll talk about the trig for chain rule is really easy, and then of course you should be able to recite the state capitals, which I cannot. Springfield, Albany, Sacramento, Reno? Right? That is Reno, isn't it? It's not Las Vegas, I know that. Montgomery? That's Alabama. Is that the capital? Yeah. Okay. Tallahassee? Okay.
We're just naming all the
Good. Yeah. Honolulu? Too easy. Is it Honolulu? Yeah. Providence, Rhode Island. There's good. Beautiful. All right, we'll come back to that in a minute. So in order to demonstrate the chain rule, I'm going to give you another example. Take that derivative, please. And then I'm going to show you a different way to take that derivative. It's going to be awesome. Again, simplify numerator. Do not simplify denominator.
Oh.
And what's the derivative of 1? Okay, good. Just checking. Trying to help. This one we seem to be in agreement on. Everybody good to go? Negative 2 over the quantity 2x minus 7 raised to the second power.
Yeah.
Or maybe you wrote it as negative 2 times the quantity 2x minus 7 to the negative 2 power. But regardless, there you go, quotient. Chain rule is a different technique that will allow us to solve a problem like this. Now, why do we care about a problem like this? Well, I can rewrite that equation the following way. Yes? Okay. So the chain rule will allow me to solve that, or take that derivative when it's in the form of 2x minus 7 to the negative first power. We've never been able to do that before because that gives me a function within a function. So I have some function that's raised to the negative 1 power, but inside of that function, I have another function. Okay? And what you're going to have to be able to do is recognize how many functions we're dealing with. That will help you in the process of solving the chain rule problems. Okay? So like I said, chain rule functions within functions, that's a chain. Great, let's go. All right, so this chart shows you problems, like it says, without chain rule that you could do now. The other one shows you problems that you would need to chain rule with because you have functions within functions. This is the chain rule. The dy over dx equals dy over du times du over dx is not crucial, but the bottom part is crucial. In English, it's this. Take the derivative of the outside function times the derivative of the inside function, and this will make more sense when we get into some examples. The reason there's a picture of an onion there is because we're going to peel the layers of the onion going from the outside in, like an ogre. Layers, like an onion. And so as we take derivatives, we're going to do this thing called chaining on as we take the derivative. And if you don't keep yourself under control, you'll just keep chaining until you go crazy. So you've got to be able to recognize how many times we're going to chain. So you see, if we have f of g of x, the question when we get into the problem is I'm going to ask you, number one, how many functions, in this case 2. I'm also going to ask you which function is on the outside. So if we go back to this example, how many functions? 2. Which one's on the inside? Which one's on the outside? The negative first or the 2x minus 7? The negative first. Great. Okay, you guys are experts. This will be cakewalk then. Okay. You're going to chain on one less time than the number of functions. Most of the chain rule problems you'll see will be 2 functions. So you'll chain once. But sometimes they'll get a little ugly. And I've got a couple of those for you today. It'll be fun. Okay, so 3 functions, chain twice. 2 functions, chain once. 1 function, chain 0. We've done those already. So let's go back to this guy and do this as a chain rule problem. So we'll forget about this function. We're just going to take the derivative of a function raised to the negative first power. Okay, so f prime of x is equal to, how do I take the derivative of something to the negative first power? Was it?
Put it 1 over 1, or under 1.
Okay, take the negative 1 out in front, then subtract 1 from negative 1 minus 1 is good, not 0. Now, 2 functions, 1 chain. So now I have to chain on, which is multiplying by the derivative of the other function, which is? Inside. The derivative of 2x minus 7 is? 2. Ooh, negative 2 over 2x minus 7 raised to the second power.
What? Wait, when did you multiply by 2?
Yeah, why do you multiply by 2?
Because that's a derivative of the 2x minus 7. It's a derivative of the inside function. That's the chain. Okay. And sometimes it'll be a number, sometimes it'll be an entirely different function. Pretty good with that.
Where's the negative 1 coming from?
What's the derivative of x cubed?
3 times x to this second.
Bring the exponent down, reduce it by 1.
Um,
Bring the exponent down, reduce it by 1.
yeah.
Okay? All right, let's try something a little bit more interesting. Well, that's pretty much the same function. Okay? Well, I'll give it to you. There it is. Done. Okay. 2 functions. How many chains? 1. Bring the exponent down, reduce it by 1. Chain on the derivative of this monster inside. So you get that. Okay. Not going to simplify. Just going to leave it alone. You do not want to cube that monster. Okay. You try that one. How many functions? 2. How many chains? 1. Do it. Don't look at me in that tone of voice. Now you can imagine why we avoided the derivative of g of x up until this point, because nobody wants to take 4x cubed plus 3 and multiply it by itself 4 times. That would be barbaric and hideous. You could do it. You wouldn't want to. Okay, we good?
Yeah.
Need a second, or are we good?
No, we're good.
Everybody? Yeah, yeah, answer. Oh, I don't have an answer. What's the answer? Oh no. Hold on. All right, give it to me.
All that cubed.
Noah, go.
4, and then in parentheses 4x cubed plus 3, close your parentheses to the 3rd power,
So far, so good.
times and 12x squared.
How do you do?
Great.
Wonderful. Good job. Easy peasy. Okay? Not so bad, right? Right? Oh. You called me out?
No.
You want 3?
I just want to see.
Hold on, I got 3 for you. Let's do I'm gonna feel a little guilty about this, but I'll get over it. This is gonna be bad. But we'll just go. We'll do it and then you'll recover. There's tissue over there if you need it. Okay, we'd like to do that. Now, the reason this is ugly is because we have a quotient rule inside a chain rule. So notice that there are 2 functions there. One is the squared function, and the other one is that division quotient, or the division function. Now, you might be saying to yourself, well, isn't that 3 functions? No, because that's still just 1 function inside. So the first part is easy. Bring the exponent down, reduce it by 1, which would be 2 times the quantity, that ugly mess, to the 1st power. The ugliness in this problem comes about from the quotient rule. And the only reason I included this is because I want to start talking about what you need to do to simplify derivatives. And like I said, simplify numerators, don't simplify denominators. Is there any part of that that you don't follow? Okay, so the first part, the 2 times the quantity 5x minus 2 over x cubed minus 3, is the derivative of the squared function. The last big set of parentheses is the quotient rule for that function inside. At that point, we're done with calculus. Now we just start doing some algebra, which gives me that. Distributed to 5, distributed to 3x squared, like terms. And then I get that. Makes sense? X cubed minus 3 times x cubed minus 3 raised to the second power is x cubed minus 3 to the third power. Excuse me. Okay, we good? Okay, now? Nothing new there. You know all this stuff. The only difference is there's a u prime on the end of it. So this is a notation that becomes fairly common. If we're taking the derivative of sine of x, we just get cosine of x. If you change the x to a u, the u implies that we're dealing with another function. So the sine of some other function would be a chain rule. Sine is on the outside. You take the derivative of sine, which is cosine of that function, and you chain on the derivative of that inside thing. So I don't even know if this is worth writing down. I just wanted to show it to you because that is technically the chain rule for those trigonometric functions.
Why do you have to do the chain rule?
Because there's part of a function inside a function that if you don't include it, gives you an invalid answer. So think about,
So if it's squared.
if we go back to this puppy, if I didn't do the chain rule, I would just get 4 times the quantity x to the 4 to the third power. We'd be missing that other component, which you would get if I took that monster and multiplied it out.
Oh.
There's pieces that we would lose.
Okay.
Okay? So let's do this guy. Two functions, one chain. Yes or no? Three functions. How many chains? Two. Which one is it? Two. What are they? Sine squared is actually 2 functions. So this is 3 functions. Which one's on the outside? The squared, the sine, or the 4x to the 5th? The squared. Remember, sine squared x is the same thing as sine x raised to the second power.
Yes.
So 3 functions.
Oh,
How many chains? 2 chains. Nice, I'm pretty proud of that.
It's pretty good.
Nice. Yeah. Okay, so the squared function is on the outside. Which one's the next layer of the onion? Sine. And therefore the center of the onion is the 4x to the 5th. Okay, go, try it. I've given you all the pieces, now put them together.
So where does the when you doing the sine function, try to get rid of where you put? Oh. When you put the square.
Out in front.
But let's put this middle part. When you put the two.
No, because 2 just there's your 2 comes down to 1.
So you just leave it.
You need one more
Oh,
chain.
in order.
Yeah.
If it helps you, you might want to think of this problem this way, because they're the same thing.
You just causing trouble?
2 chains?
2 chains?
Got it? Let's check. What do you got?
2.
No. Audrey?
Got 2 sines, 4x to the 5th.
Uh-huh.
Cosine, 4x to the 5th.
Uh-huh.
20x to the 4th.
How'd she do?
Good.
It's perfect.
I just didn't have the 4x to the 5th, the sine and cosine.
It stays with the function. So you don't, when you work with those functions and you build your way, you work your way inside, the other parts of the function have to stay with it. So this is still reduced it by 1, or brought down in front, reduced it by 1. That thing stays together as one unit. Then when you take the derivative of the sine of that thing, you're taking the derivative of that thing is the cosine of that thing. You understand what I mean? Is everybody good on that? Okay. And then that last bit is the second chain, which is a derivative of that. And you can clean that up a little bit by moving the 20x to the fourth out in front to get 40x to the fourth times the sine of 4x to the fifth times the cosine of 4x to the fifth.
I'm also confused. How did we for sure know that the square is the outside one?
Because of that. Okay. And the reason I included this is because I was sure that that was going to cause some problems for people. That remember that this is the same thing as this, which is not the same thing as this, right?
Oh, then it's x squared.
Yeah, this is actually the same thing as that. We don't care about this. We care about these guys. Okay? It will take some practice. But one of the important things about recognizing how many chains you need is if I go back to this problem, for instance, this one here, if you're not careful and you just keep chaining, now all of a sudden I take the chain of that and I get a quadratic, then I take the chain of that and I get a linear, then I take the chain of that, I get a and eventually I'm going to get down to 0. So you have to be cognizant of how many functions you have versus how many chains you need, and stop after that many chains. It's going to be tempting to keep going here because I know how much you love doing derivatives, but you have to stop when you get to the number of chains. That's one mistake. The other mistake is not doing enough chains. For instance, not recognizing that this is 3 functions, not just 2. Okay? We good? Think you can handle it? Again, practice. So as you get into the homework, and the homework will start to ramp up. So you'll start with some very basic chain rule problems, and then as you get to the later problems, they'll get a little bit nastier. You can handle it. This is a summary of all the derivative tools that we've had so far. There's one more that I'll teach you on Tuesday called implicit differentiation. It's not that hard, but power rule, product rule, quotient rule, chain rule. It's pretty much all you need to take the derivative of just about any function. Okay? We good? Awesome.
I don't really understand like homework, like what it means. It means like plus 3.
Every third problem.
What?
Every third problem. 3, 6, 9.